the last topic we're going to discuss in this chapter deals with two types of nuclear reactions. We have what is known as nuclear fission and nuclear fusion. All right. So let's talk about fission first. In the case of nuclear fission, what actually happens is that you have a large nucleus which is bombarded with a small particle like an alpha particle or a neutron or something like that. The result of that bombardment is that the nucleus, the large nucleus, is split into smaller nuclei and also produces other particles like neutrons. And what also happens along with this is large amounts of energy are released. All right, so a good example of this is the bombardment of uranium 235 with neutrons. And this is what happens. When the neutron is bombarding the uranium 235, it forms an unstable nucleus, uranium 236, which spontaneously breaks down to form krypton 91 and barium 142, along with three other neutrons. All right. So, also, very important, a large release of energy occurs as well. All right. So that's what happens. This is just one example, and there are several other examples that one can point to of nuclear fission. So what they all have in common is that you have a large nucleus being broken up into smaller nuclei, and some other particles are produced as well, along with, as I said before, a huge release of energy as well. So to balance these equations, it's pretty much the same as what we were discussing before. So this question is asking for basically the identity of that particular nucleus. So we have to add up the total number of neutrons, or I should say the total mass number and atomic numbers on both sides. So let's do that now. In the case of the atomic numbers, the sum is 92, 92 plus 0 on the left. We have 52 here, we have 0 here. So that means that as far as this unknown entity is concerned, the atomic number would be 40. All right, because 40 plus 92 would give you, 40 plus 52 would give you 92. Now, let's look at what happens as far as the mass number is concerned. As far as the mass number is concerned, the total on this side would be 236. Now here we have 137, and here we have 1 here, but we have this 2 here. So 2 times 1 gives you 2. So 2 plus 137 give you 139, which means that the mass number for X would be 236 minus 139, and I got 97 right here, right? So basically, all we have to do now is consult the periodic table and look for the element with the atomic number 40. And when I do that, I see that the element that has atomic number 40 is zirconium, symbolized by ZR. So therefore, this would be what X is. X would be zirconium 90. All right? So that's basically how we do that. So it's very similar to what we saw before when it comes to balancing equations in the previous examples. Okay. Now, what often happens in these fission reactions is that you have a chain reaction. And let me use the example of the bombardment of uranium 235 as an example, which is an example that we saw before. So basically, when the first bombardment takes place, as we said before, the uranium 235 splits up to form these two smaller nuclei along with 3 other neutrons. And then if you have more material present, more uranium 235 nuclei present, then these 3 particles will bombard these 3 uranium nuclei to form basically the same particles as before. And this goes on and on and on if you have enough uranium material, all right? And this produces energy in each step. So therefore, by the time all of it reacts, a lot of energy is produced, okay? In fact, the energy that is produced can be so large that even an explosion will take place. But this will only happen if you have enough uranium material. So there's a term that is used in this particular context. It's called a critical mass, right? Basically, what you need in order for this chain reaction to occur is that you have a minimum amount which supplies enough uranium that will undergo these bombardments um, repeatedly in a chain reaction to produce energy, right? If you don't have that critical mass, then this will not happen. Basically the chain reaction will stop too soon, and therefore you don't have as large a release of energy occurring. All right. So that's what happens, for example, in nuclear power plants, such as the one that used to be in Crystal River some years ago, but they decommissioned it for whatever reason, I don't know. But basically, what you're looking at here is the basis or the schematic representation of what happens in a power plant. Right in here is where you have the reaction taking place between the uranium 235 and the neutrons, right? And you can control the flow of the neutrons by using these control rods, which, if I remember correctly, are made up of graphite. So basically, this is where the reaction takes place. A lot of heat is generated, which is transferred here to where we have a steam generator here, which contains water. This is usually obtained from some river source, which I think is what happened in the case of Crystal River. So basically, that energy is used to convert the water to steam, and the steam is transported to a steam turbine. So the energy of the steam is basically converted to electrical energy, which is fed to the external grid, right? And there's some recycling of water that takes place because the steam that comes down here is cooled. Some of it is passed back to the river, which can cause some environmental issues in terms of thermal pollution of waterways. Aquatic life can be affected. But then you can get some of the water, which is cooled, to go back into this reservoir here, the steam generator, and basically you can recycle the amount of water used for this purpose. So that's basically how the nuclear power plants really works. All right. Okay. Now let's talk about fusion. Now fusion is basically where you have two smaller nuclei coming together to form a larger nuclei. And this also corresponds to a large release of energy, such as the reaction between hydrogen 2 and hydrogen 3 isotopes to form the alpha particle. A neutron is produced as well, and a lot of energy. This is the reaction that takes place continuously in celestial bodies like the sun and stars. All right. So the energy that is emitted, for example, from the sun that we receive down here on Earth is basically as a result of fusion reactions such as these. And in fact, there are scientists who have been working on replicating these reactions on Earth as a source of energy, and there's been some success recently, which I won't go into right now, but basically there are some scientists, government scientists, who have been successful in actually replicating the same nuclear reaction, fusion reaction that takes place in the sun. Of course, sophisticated instruments and apparatus were used to do that. So, the next step is to get something a bit more compact and convenient that can serve as an energy source alternative to fossil fuels. All right. So that's something that is in the works as we speak. All right. Okay. So let's see if we can answer these questions here. It says indicate if each of the following describes either nuclear fission or nuclear fusion. So in the case of a nuclear splits, the answer would be nuclear fission, right? Because that's what happens when a large nucleus is bombarded by small particles. In the case of B, large amounts of energy are released. The answer would actually be 1 and 2, right? In both cases, huge amounts of energy is released. In the case of C, small nuclei form larger nuclei. The answer would be 2, nuclear fusion, all right? And then in the case of D, hydrogen nuclei react. Now that's an interesting one. Hydrogen nuclei react. That is fusion actually. I'm thinking of the example that we just saw between hydrogen 3 and hydrogen 2. And then the last one, several neutrons are released. Well, that would be the nuclear fission that we saw earlier. Remember when the uranium 235 is bombarded with a neutron, and then basically you have, in addition to 2 smaller fragments, you have 3 neutrons being produced. So those are the answers for these questions. All right. And that's basically it for this video. All right, so for the next class, we'll be dealing with questions based on this topic or this chapter. All right? Okay, until next time.